Stangibelisco here, proprietor and operator of amateur radio station W1 GV, Whiskey 1 Good Vibrations. Here to talk just for a minute about Earth, or Moonbounce communications. Most people recognize it as Moonbounce. Of course, as you might imagine, you need a high power transmitter, a high gain antenna, and a sensitive receiver at both ends of the circuit, this end and this end. Of course, this is the Earth, this is the Moon, and this is a theoretical or hypothetical communications path. The distance to the Moon from the Earth is about 250,000 miles. So a round trip is about 500,000 miles. Now if light travels and radio waves travel at 186,000 miles per second, then a complete trip from station, well, let's call it station A up here at the top and station B down at the bottom, 500,000 divided by 186,000. Or about 2.7 seconds. So when station A sends da, call this station A, station B won't hear it until 2.7 seconds later. Remember the old Apollo missions back in the 60s and 70s, and why there was this strange delay? They'd say, main control, how are you doing up there? Well, we just landed. But between the main control, how are you doing up there, and, well, we just landed, you'd hear a 2.7 second delay minimum. More like 3 seconds, because it takes a bit of time for the person to react to the question. Well, this is the way that it would work in the theoretical, simplistic sense. A single path, and you'd hear a weak signal. But, provided that you had the appropriate equipment, the most common frequencies being 144 megahertz and 432 megahertz, you'd just hear a very weak signal, and it would always be Morse code because that's the signal that's the easiest to copy under adverse conditions. And if these conditions aren't adverse, I don't know what is. But that's just a part of it. The Moon is constantly wobbling back and forth with respect to the Earth, or as seen from the Earth as it orbits around. And signals don't just travel a single path like this. Signals travel many, many, many paths, because they reflect off of every mountain, every crater, hundreds of places, and all of these different reflections combine in various phases when they return to station B from station A, and the result is a fluttery sound, a fading called libration fading. Not libation, not liberation, but libration, which refers to that wobbling of the Moon as seen from the Earth. Those multiple signals that arrive back in constantly shifting phase produce a fluttering, fading, similar to the fading that you hear with auroral propagation. So that the only mode that's of any practical use for this kind of communications is good old-fashioned CW. Even phase shift keying or frequency shift keying won't work. You need CW, and it has to be relatively slow because of the intensity of this fading. That is libration fading, and it's unavoidable. There's no way to get around it. That, on top of a weak signal, makes for very challenging conditions indeed, and you need very expensive equipment in order to transmit and receive these kinds of signals. But it has been done by ham radio operators for decades. And to some extent, sorry about that cough, we will also hear signals at 1296 megahertz. The higher the frequency, the worse the libration fading in general, because the shorter the wavelength, the greater the number of fades. But even if the wavelength were on the order of 20 meters or 40 meters, you'd still have libration fading. So that's what libration fading is. When you hear them talk about that in respect to Moonbounce or Earth-Moon-Earth, EME communications, that's what they're referring to. This kind of fluttery sound that you're going to hear on the received signals. Stan Jabalisco, proprietor and operator of amateur radio station W1GV, saying 73 for now, which of course means best regards, and so long, which in EME communications would come out as did-da, minus the flutter, of course. I can't imitate that. So long.